So back in 2019, this massive financial institution left a single, well, metaphorical backdoor open in their cloud environment.
Right, just one little misconfiguration.
Exactly. Just one misconfiguration and boom, over 100 million credit card applications were exposed. And the crazy thing is, it wasn't some like sophisticated Ocean's 11 style heist.
No, not at all. It was literally just a failure to properly define the virtual boundaries of their network.
Yeah, and that is exactly what we are tackling today. Welcome to the deep dive. If you're joining us, we are looking at study materials for the AWS Cloud Practitioner Certification. Specifically, we're getting into the notoriously tricky Module 5, which covers VPCs, subnets, and firewalls.
Oh, yes. The heavy stuff.
The really heavy stuff. And, whether you're prepping for this exam yourself or you're just trying to translate what your IT team is constantly arguing about in Slack, or maybe you just want to understand how the internet's back end actually stays secure, this deep dive is going to make all those abstract concepts really concrete for you.
Absolutely, because to really understand this, we have to move way past all the acronyms. Cloud networking sounds like this massive alphabet soup of IT jargon, right?
Totally. AWS, VPC, IGW. It's a lot.
It is a lot. But the underlying engineering constraints are actually fascinating once you break them down. The entire AWS infrastructure relies on this concept called software-defined networking. And to visualize that today, we are going to build a highly secured, master-planned, gated community.
Okay, I love this framework. Let's do it.
Yeah.
So let's look at the absolute baseline first. Before we can start, erecting buildings or hiring security guards for our gated community, we have to actually draw the physical property lines.
Right, the foundation.
Yeah. And in AWS, the notes call this the VPC, the virtual private cloud. Basically, it's your isolated slice of the cloud. But here's what always trips me up when I look at cloud architecture. AWS is a public cloud.
Yes, it is.
So you and I, and potentially our biggest business competitors, we're all sharing the exact same physical servers in some massive data center out in Virginia, right? So how is a VPC actually isolated if we're all on the same hardware?
Well, that is kind of the core paradox of cloud computing. You are sharing physical hardware, but you are mathematically isolated at the network virtualization layer.
Mathematically isolated.
Yeah, so when you create a VPC, you're defining a specific range of IP addresses for your environment. And the hypervisor, which is just the software that runs the physical servers, it uses packet encapsulation to make sure your data is tagged and completely separated from everyone else's.
Okay. So it's like a virtually dedicated space.
Exactly. Your virtual environment operates as if it were a totally dedicated physical data center. And I mean, if that mathematical boundary fails, your data is essentially just sitting out in a public square.
Wow. Okay, so that makes the VPC the walled neighborhood itself. But inside that neighborhood, the source material divides the VPC into subnets, specifically public and private subnets.
Yes, the internal zones.
Right. So if the VPC is the walled neighborhood, the subnets are like the zoning laws. The public subnet is like the community clubhouse or the leasing office right at the front where anyone can walk in. And the private subnet is the cluster of houses tucked way in the back where only residents are allowed.
That's a great way to picture it.
But wait, from an actual engineering standpoint, what makes a subnet public or private? Because I'm assuming it's not just like a checkbox you click in a menu.
No, it's not just a checkbox. It actually all comes down to routing. A subnet is really just a smaller partitioned block of IP addresses inside your VPC. What dictates whether it's public or private is its routing table.
Okay, the routing table.
Yeah. Think of the routing table as the GPS navigation system for that specific zone of the neighborhood. If the routing table has a path that leads directly out to the public internet, then boom, it's a public subnet.
And if it doesn't?
If the routing table has absolutely no physical mapping to the outside world, it is a private subnet.
So it's literally just about the roads. Like if we build a web application, those web servers are acting as our storefront. They have to live in the public subnet because our customers need a road to actually reach them.
Exactly.
But the database that holds all the credit card transactions, the vault, basically, that lives in the private subnet, it just straight up does not have a road connecting it to the outside world.
Precisely. Because the general public should never, ever be able to directly route a packet to your database. That separation of presentation from data storage is basically the whole foundation of cloud network architecture.
Okay, so we've established the walls and the internal zoning.
Yeah.
But, I mean, a walled neighborhood isn't very useful if no traffic can ever actually enter or leave, right? We need a secure way to cross that perimeter.
Yeah, we definitely need doors, and that's where gateways come in. This is actually where the routing tables we just talked about send the traffic.
Yeah, so the study notes emphasize two major gateways, and they point out that these are constantly tested on the exam. There's the Internet Gateway, or IGW, and the NAT Gateway. Let's start with the Internet Gateway.
Sure.
If I have a web server in my public subnet, its routing table points all outbound Internet traffic to the IGW. So this acts as the main front door of the neighborhood.
Yeah, and it really acts as a two-way street. When a customer types your website into their browser, that request enters through the Internet Gateway. The IGW looks at the packet, maps the public IP address to your server's private IP address inside the VPC, and then just forwards it in.
And then when the server replies,
When your server replies with the web page, the traffic goes right back out that exact same door. Honestly, without the IGW attached to your VPC, your public subnets are entirely cut off from the outside world.
okay, that part feels pretty intuitive. Front gate, open for business. But the NAT gateway, that one is flagged in these notes as a massive exam trap.
Oh, it really is. It catches so many people.
The source describes it as a one-way exit that is strictly for private subnets. Let me challenge the logic here for a second. We just said private subnets don't have roads to the internet. Why on earth would my highly secured, totally isolated database ever need to connect to the public web?
Well, think about routine maintenance. Let's say your database operating system suddenly requires a critical security patch from an external vendor. The database has to initiate an outbound connection to the internet to download that patch.
Right. But wait, if I just temporarily point my private database's routing table to the internet gateway so I can download the patch?
Then you've just turned your private subnet into a public subnet.
Oh.
Yeah. By doing that, you have literally given the entire internet a bidirectional map straight to your vault. And that is the exact trap that, 80% of test takers fall for.
Okay, wow. So to make sure I have this right, that is where the NAT gateway comes in. I'm visualizing it like a one-way mail chute or maybe a secure turnstile.
Yes, exactly.
So my private database can push a request out through the turnstile to grab a software update. But a hacker on the outside can't use that same turnstile to walk back in.
Spot on.
But how does that actually work mechanically? I mean, if my database is completely private and hidden, how does the software update know where to go when the patch comes back?
Well, the mechanism is called network address translation, specifically port address translation. When your database sends a request to the internet, it first routes that packet to the NAT gateway, which actually sits in the public subnet.
Oh, the NAT gateway is in the public subnet.
Yes, and it does something very clever. It strips away the database's private IP address from the packet header, and it slaps its own public IP address on the envelope instead.
Like a proxy.
Yeah.
So the external web server hosting the patch only ever sees the NAT gateway. It has absolutely zero knowledge that the private database even exists.
Exactly. The NAT gateway keeps this internal ledger a state table. When the patch gets sent back, it arrives at the NAT gateway. The gateway checks its ledger, sees that your private database initiated this specific request, and then quietly forwards the data back into the private subnet.
That's incredibly smart.
Right. And if malicious traffic just randomly tries to initiate a connection from the outside, the NAT gateway drops the packet immediately. It basically says, there's no entry in my ledger for this. You cannot come in.
That is brilliant.
Oh.
Okay, so we have a secure path to the internet. But a path is really just a wire. I mean, a physical door is useless if literally anyone can just walk through it.
Major.
So how does the network actually discriminate between, valid user traffic and a brute force attack? That brings us to the active security personnel, which the notes call the single most tested topic in this entire domain, packet filtering.
Yeah, this is where we transition from physical boundaries to pure logical rules. We have to evaluate every single packet of data moving across the wire.
And the source material introduces two distinct layers of defense here. We have security groups and network access control lists, or NACLs.
Yes, SGs and NACL.
Let me bring in the analogy the notes use for this because I think the distinction is super vital. The NACL is the checkpoint guard standing at the neighborhood gate, checking everyone driving down the street, while the security group is the personal bodyguard standing directly in front of a single specific house.
That is a perfect visualization of the scope. Security groups operate at the individual instance level. You attach them directly to your individual servers, whereas NACLs operate at the broader subnet level. They protect the entire street or zone.
Okay, but the notes use some pretty heavy jargon here to differentiate how these guards behave. They state that security groups are stateful and only support allow rules, while NACLs are stateless and support both allow and deny rules.
Right, those are the key words.
But wait, what does stateful actually mean for our personal bodyguard? Is that related to that ledger you mentioned with the NAT gateway?
It is entirely about the ledger. Stateful means the security group actively tracks the state of every connection in a tracking table within the hypervisor.
Okay, so what does that look like in practice?
Let's look at the mechanism. If your server initiates a request to the internet, the security group logs that connection state. When the response traffic tries to come back in, the security group automatically allows it, regardless of whatever your inbound rules are, because it remembers the outgoing request.
Oh, so it has a memory. Like if I leave my house to go to the store, my bodyguard remembers my face. When I come back an hour later with groceries, he doesn't tackle me to the ground to check my ID. He just knows I just left.
Exactly. That connection tracking is what makes security groups so powerful and, honestly, relatively easy to manage. Now, contrast that with the stateless packet filtering, which applies to the NACL, the checkpoint guard at the end of the street. Stateless means there is no ledger. There is no memory.
So the guard basically has the memory of a goldfish.
A very strict, unyielding goldfish. The NACL evaluates every single packet in total isolation. It checks your ID when you enter the street, and if you try to leave the street 5 seconds later, it has absolutely no idea who you are. It is going to rigorously check your ID again against its outbound rules.
Wait, let me pause here because that seems like a total nightmare for IT administrators.
Oh, it can be.
Like if I'm running a public web server and I write an inbound NACL rule that allows internet traffic on port 80,
Yeah.
the standard web port, so users can request my homepage. If the NACL is stateless, doesn't that mean I also have to explicitly write an outbound rule allowing the web page to travel back to the user?
You do, and this is exactly where network engineers earn their paychecks. When a user requests your web page on port 80, your server actually doesn't respond on port 80.
It doesn't.
No. It dynamically opens a high-numbered temporary port called an ephemeral port, usually somewhere between 2024 and 65535, just to send the data back.
Hold on. You are telling me that because the NACL has no memory of the connection, I have to explicitly write a rule that leaves tens of thousands of outbound ports open just so my server can respond to a basic web request.
That is the reality of stateless firewalls.
Yeah.
You have to explicitly define the ephemeral port ranges for return traffic. It requires a much deeper understanding of how TCP/IP traffic actually flows.
Wow. Okay, well, that makes the whole allow versus deny rule distinction make a lot more sense. The notes, state security groups only have allow rules. And since it's a personal bodyguard, it operates strictly on a VIP list.
Right. Default deny.
Yeah. If you aren't explicitly on the allow list, you are just invisible. You cannot write a rule in a security group that says, like, block Dave. You just don't put Dave on the list.
Exactly. It's a default deny posture. But the NACL, the checkpoint guard down at the street, that supports both allow and explicit deny rules.
So if there is a massive botnet out there, like a known malicious block of IP addresses just hammering my web servers, I don't want my individual security groups having to silently ignore millions of packets. I want to ban them at the street level.
Exactly.
I go to the NACL and I write a hard deny rule for those specific IPs.
That's it. You drop the malicious traffic at the subnet boundary before it ever even consumes compute resources on your actual instances. That layered approach, using the stateless checkpoint to catch the broad attacks and the stateful bodyguard to enforce the specific application rules, that is the very core of defense in depth.
This architecture is incredibly robust. I mean, we have our perfectly secure self-contained community, but enterprise networking rarely exists in a total vacuum, right? Like what happens when our company acquires another startup? Or what if the finance department has their own completely separate VPC and our web application VPC needs to securely pull data from them?
Well, you certainly don't want to route that traffic all the way out through the internet gateway and back in again. Sending internal corporate data over the public internet is slow, it's expensive, and it's a massive security risk. Instead, you use VPC peering.
VPC peering. The study guide defines that as a direct networking connection between two VPCs, using AWS's private infrastructure to route traffic between them.
Yes, exactly.
So it's basically two neighborhoods, and we build a private road directly between them. But the absolute loudest warning in this entire module is this one specific limitation. The notes say VPC peering is non-transitive.
Right. And transitivity in routing protocols is a huge concept. Honestly, if you understand why AWS forces non-transitive peering, you really understand cloud security.
Let me try to translate this limitation. Here's where it gets really interesting for you listening. It's basically like a VIP guest list. If VPCA is my neighborhood and I bill a private road to VPCB, we are peered. We can share data. But let's say VPCB is also peered with VPCC. Just because I trust B and B trusts C, that does not mean C can use their key to crash my neighborhood, right? Connections are strictly one-to-one, so A and C cannot communicate.
That is exactly right. To understand why, you have to look at the blast radius. If cloud networks utilize transitive routing by default, you would essentially create a terrifying invisible web of access.
Oh, I can see that.
Yeah. Imagine you peer your VPC with a trusted third-party analytics vendor, but what if that vendor has peered their network with 50 other clients? Suddenly you have inadvertently exposed your architecture to thousands of totally unknown servers.
Oh, wow. So a single compromised server, like 3 degrees of separation away, could just daisy chain its way straight into my private subnet.
Precisely. By enforcing non-transitive peering, AWS completely removes the possibility of accidental routing loops and massive security breaches. Every single relationship must be explicitly defined.
So no shortcuts.
No shortcuts. If VPCA needs to talk to VPCC, the network administrator must deliberately build a brand new dedicated peering connection between them and update the routing tables in both environments to allow them to communicate.
Okay, I feel like we have successfully mapped the mechanics of this whole architecture.
Yeah.
But, knowing the theory and surviving the actual exam are two very different things.
Oh, absolutely.
The source notes provided 3 real-world scenario traps to prove you actually grasp how these components interact. So I'm going to play the role of the test taker here alongside the listener. I'll walk through my logic, and you tell me if I pass or if I just, exposed all our data to the dark web.
All right, let's put your gated community to the test. Let's hear the first one.
Okay, scenario 1. You have a database in a private subnet that must download a security patch from the internet, but it must remain completely invisible to outside internet traffic. Which gateway do you use?
Okay, what's your thought process?
Well, I'm looking at this. It needs internet access. The Internet Gateway provides internet access. So if I just temporarily attach an IGW and modify the routing table...
And you just failed the exam.
Because I made it a two-way street. I gave it a public route.
You did. The Internet Gateway is the classic trap here. A private subnet with an IGW is no longer a private subnet. To allow outbound-only traffic while stripping the database's internal IP address, you must use the NAT gateway.
Right, because it acts as the stateful proxy, managing the ephemeral ports, and securely returning the traffic.
Spot on. Okay, what's next?
Okay, fair enough. Scenario 2. You notice a specific malicious IP address launching a denial of service attack against your servers, and you need to explicitly block it. Which firewall do you configure? My first instinct here is the security group because it's attached directly to the server that's being attacked. I want my personal bodyguard to handle it.
You are falling for the traps again. Think back to the rules of the bodyguard.
Wait, security groups only support allow rules. They operate on a default deny VIP list basis.
Exactly.
So I literally cannot write a rule in a security group that explicitly says block this specific IP. It will just silently ignore the traffic, which means the malicious packets are still reaching the instance level. If I want an explicit deny rule, I have to go out to the street level.
Spot on again. You must use the stateless NACL at the subnet level. The exam loves testing this distinction because, our brains just default to thinking of firewalls as things that block traffic. But in AWS, the stateful security group is an allow list, while a stateless NACL is your tool for explicit denial.
All right, final test. Scenario 3. VPCA is peered with VPCB. VPCB is peered with VPCC. You are a systems administrator, and you notice instances in VPCA cannot communicate with instances in VPCC. What is the most likely cause?
Let's see if you remember.
Well, I know this one now. The exam will probably try to tempt me with answers about misconfigured security groups or broken routing tables. But the architectural truth is that VPC peering is strictly non-transitive. They cannot communicate because a direct peer does not exist.
Flawless. They will absolutely throw paragraphs of technical distraction at you to make you think it's a packet filtering issue. But you really have to recognize the structural geometry of the network. Without that direct peering connection, communication is impossible by default.
Awesome. We mapped the entire network. Let's zoom out real quick and recap what we've built for you. We started with the chaotic public cloud, and we carved out our mathematical boundaries using the VPC.
Right.
Then we organized that space with routing tables, creating public subnets for our web servers, and isolated private subnets for our databases.
And then we managed the traffic flow using our gateways. The Internet Gateway for bidirectional public access, and the NAT Gateway for secure, port-translated outbound requests from our private resources.
And we layered our defense. We hired the stateless NACLs to check packets against hard allow and deny rules at the subnet boundary, and we put the stateful security groups to track connection states right at the instance level.
And finally, we connected our environments using non-transitive VPC peering to maintain a contained blast radius.
Which means what you have now isn't just, flashcard knowledge. You possess a really comprehensive mental model that cuts through the thickest IT jargon.
Yeah.
You can actually visualize exactly how packets physically navigate a cloud architecture.
Exactly. When you understand the actual mechanisms, the routing tables, the state tracking, the ephemeral ports cloud networking stops being abstract.
It becomes something you can actually visualize step by step. But,
Yeah.
diving this deep into how meticulously we build these virtual walls makes me wonder about the future.
Yeah.
We put so much effort into defining these rigid network perimeters, VPCs, subnets, gateways.
It really does raise a provocative question about the evolution of network engineering because, everything we just discussed relies heavily on managing scarce IP addresses and building trusted internal networks.
Right.
But as the industry shifts toward IPv6, where literally every single device has a unique, globally routable address, and as we embrace things like Beyond Corp or Zero Trust architecture.
Oh, where the network itself is considered entirely hostile no matter what subnet you're in.
Exactly. It makes you wonder, in 10 years, will the entire concept of the virtual private cloud and the NAT gateway just become totally obsolete? Will we eventually abandon the idea of a secure network perimeter altogether and instead rely entirely on strict cryptographic identity verification at the software layer?
Wow. The idea that the gated community itself might just disappear, leaving every house sitting directly on the public street, relying purely on unbreakable cryptographic locks. That completely changes how you think about cloud architecture.
It really does. It's a fascinating shift.
It gives us all something big to mull over. But hey, until that day comes, at least we know exactly how to configure the checkpoints. Thanks for diving in with us, and we'll catch you on the next deep dive.